So if we assume, I'm recapitulating, if we assume that under a gauge transformation, a very specific gauge transformation, in which phi remains unchanged, but A goes to A plus gradient of lambda, if under these transformation, my state changes by G of, G times the state, then what happens is, the Schrodinger equation, what does happen to the Schrodinger equation? The Schrodinger equation is IH bar the time derivative of psi minus the Hamiltonian, right? What is the Hamiltonian? It's P minus Q by CA divided by 2m, and there's a squared here, minus Q of phi acting on psi is equal to 0, right? That's the Schrodinger equation. So under the gauge transformation, what happens is if we have IH bar d by dt, psi becomes multiplied by g, but we are assuming that our gauge transformation is time independent. So it's going to go through the time derivative. Inside, we showed that the operator, this guy goes like what we can do here is we can say this can be, we can have G here and then G dagger, which is 1. And here we have P minus Q by CA squared by 2m minus Q of phi. But here we have G of psi equals to 0. And then we can just take this outside because G does not depend on time. So we have IH bar d by dt of psi. Here, we can get this guy outside. We have psi, and then we have hang on. Do we have the psi, and then we have here G dagger P minus Q over C. এখানে হচ্ছে কি we have the new A tilde, right? That's something I forgot. There should be the A tilde, and then we have G here, and over here we have Q phi times psi is 0. Now, if I multiply this equation on the left by G inverse, then that cancels this guy and this guy. And we know that this thing is, by construction, over here, this thing changes, this thing down back to the original gauge, gauge choice, and therefore I have IH bar del psi by del t minus P. There should be a squared here. Of course, I mean, if you have an action on a operator like this, then this is the same thing as G dagger G. This is the inverse of G, A of G. So the fact that there's a square here is not a problem. And then this becomes P minus Q over C, A squared, and then minus Q of phi of psi is 0. So thus we see that the gauge transformation, under the gauge transformation, if the state changes in this way, where G is defined by this thing, then the Schrodinger equation is invariant. Okay? So we see that the Schrodinger equation remains invariant. Okay? Is this clear? Maybe the details may not stay, be clear at this point, but the gist is that gauge transformation leaves the Schrodinger equation invariant. Okay. Any questions? Do you want me to go through it again?
Yeah, that would be a bit good.
Okay. So let me just recapitulate the whole thing. Okay. So the idea is that we want to see if how the Schrodinger equation behaves under this gauge transformation. Okay. So this gauge transformation is that we are doing a special gauge transformation in which the gauge function, this is called a gauge function, lambda is time independent. You can do it for more general, but we won't need that. So I'm just like doing the special case. But this is complicated enough. So phi, we're not going to change it, but A, we are going to change it by the gradient of lambda. But physically, our physical observables in physics are expectation values. So we are going to say expectation value of the position operator is going to be invariant under gauge transformation. And the position and the expectation value of the kinematic momentum, which is a measurable quantity, it's a momentum of the particle and the field combined, that is also going to be invariant. But we know that A is not invariant, so we know that something has to give. So we have to assume that under the gauge transformation, the state cannot remain the same. So we assume that the state changes under gauge transformation by some operator called G, calligraphic G acting on the original state. Okay? Is this clear so far?
Yes, sir.
Okay. So now, what are the requirements that G has to satisfy? So first, let's take this guy. This guy is going to tell us that, well, alpha tilde is G times alpha, and alpha tilde bra is alpha G dagger. And therefore, this has to be equal to this thing. So this has to be equal to this. But you see, this guy, alpha, is just a random state. So for this to be true, it has to be true as an operator equation. So this is one of the requirements, okay, for G to satisfy.
Yeah.
So similarly, from this equation, from the requirement that the kinematical momentum be invariant, gauge invariant, we find this equation. Okay, so this guy is nothing but this thing with the gauge transformation. So A changes by this gradient, right? And then, what I'm saying is that if I take this calligraphic G to this exponential, this function, where this is the gauge function, then both of these, both of these things are satisfied. And that is a small computation that you do, okay? Is that clear?
Yes, sir.
Okay. So now, let's go back and see what effect this has on the Schrodinger equation. So this is the Schrodinger equation. If I make a gauge transformation, my state changes by G acting on this. So here I have G acting on my state, G acting on my state. Now A will change to A tilde. So this is a shorthand for A plus gradient of lambda, okay?
Yeah.
Okay, and now now you see, if I look at the form of G is just is a phase, right? If I look at the form of G is nothing but a phase. It's a position-dependent phase, okay? Exponential of this, it's a phase, right? But it depends on the position. So, because it's a phase, I can insert the phase and its conjugate here. This is 1. Do you agree?
Yeah.
Yeah. So now, but the phase depends only on space, so the time derivative doesn't do anything on it. So I can pull out the time derivative outside, and I can also pull out one of the g's from the bracket here. And then what we have here is G inverse, whatever the operator is squared, G. Okay? Because I'm also multiplying this thing inside. So this thing, and then, so this thing is going to multiply this from the right. So, but this cancels out because we can just multiply by G inverse from the left. So this goes away. And what is this? This is just, according to the invariance property of G, this is just this thing without the tilde. And here I'm using the fact that, we have P minus Q by C, A dagger, A tilde, G dagger G is equal to P minus Q by CA, right? This is something we proved above, but this also means that we can square it and it is still going to be valid, right? And that's because if I have an equation where G dagger A, A is not a good, say chi hat, G is chi hat, then if I take G dagger chi hat squared of G, then I can write this as G dagger chi G dagger, because this is 1 chi hat of G. So according to this, I can apply this twice, chi times chi, so I get chi squared. So, right? So is this clear why this is true?
Yes, sir. Yeah.
So thus we see that the Schrodinger equation is gauge invariant, even though it's written in terms of the gauge potential, because the way that the wave function changes. Okay?
Yeah.
Okay, so I'm going to stop here, and in the next class, we will go to Aharonov-Bohm effect. The Aharonov-Bohm effect can be analyzed using Schrodinger equation, but we are going to do it using path integrals, okay? Because we now have more than one tool in our toolbox. And we want to show off our skill set, okay? Any questions?
Sir, so this linear transformation G, so we basically, before even started working, had to choose one particular one, right? By some inspection or something. Like,
Sorry, can you repeat that question again?
I mean this about this linear transformation G. So we basically wrote it as exponential of some function, null
Yeah.
operator. So was it by inspection, like that we wrote it in such a way that our conditions that it gives the expectation values invariance. And
Yeah. I can even I could have given you as an exercise and you would have figured it out. You would have figured out that function needs to be the gauge function.
oh, okay.
And Young and Mills did exactly that. Young and Mills did a non-abelian generalization of this, and they got the Nobel Prize for discovering the Young-Mills theory, which is the theory that. No, I don't think Young-Mills got the Nobel Prize for that. But Young-Mills theory they did exactly this, but for a more complicated case where instead of the phase, the gauge transformation is more complicated. It is a non-abelian group. You can show that this is actually an abelian group, right? Because, for example, the phases. So if I make two gauge transformations, say e to the power I theta 1, and then e to the power I theta 2, then e to the power I theta 1 plus theta 2, that is also a gauge transformation, right? Where these are basically, I should use lambda really. If I take one gauge function, lambda 1, another gauge function, if I do two gauge transformation one after another, you can show that is also a gauge transformation. In this case, the combined gauge transformation, the gauge function is given by lambda 1 plus lambda 2. Now, this is the multiplication law for an abelian group called U1, right? But you can actually generalize this to a matrix equation for, say, SU2, SU3, all kinds of non-abelian groups. To find the equation that is invariant under these non-abelian gauge transformation is something that Young and Mills worked out, and they did exactly what Nahi was saying. They worked backwards. They figured out how they transform. If you want, it's a very beautiful paper, the one by Young and Mills. When we were doing master students at Dhaka University, our teacher, Professor Lalit Nath, who was a student of Higgs, he made us read the paper actually. So yeah, but yeah, now you're right. Somebody did a back calculation.